Hi everybody, so today we're going to talk about graphing polynomials. So the first technique we're going to use, you can only use when you have a polynomial that has the form y equals x to the n, okay, or a transformation of that form, okay. So we're going to use the base graphs and transformations. Now we don't know all the base graphs, right? We don't know every base graph for x to the n. So we're going to use two basic base graphs. So if n is even, okay, we're going to use the y equals x squared base graph. Okay, and then if n is odd, we're going to use y equals x cubed. Okay, so those give you the basic shape of the graph, and then you're going to use the transformations to get a more accurate picture of the graph. So let's look at an example. Okay, so first of all, we need to look at the exponent to determine the degree. So obviously here our exponent is 4, which is even. Okay, so we're going to use the y equals x squared graph. Okay, then we're going to look at the transformations. So this plus 3 here on the inside of the function is going to move the graph left 3. Okay, and then if you look at this plus 1, that's going to move the graph up 1. Okay, so the final thing we need to do before we make our graph is to look at our base graph. Okay, so just to remind you, here's our base graph, and our key points are 0, 0, 1, 1, and negative 1, 1. Okay, so we're going to take that base graph and then we're going to use our transformations. Okay, so here's what my actual graph would look like. Okay, so we're going to take the vertex of our base graph and move it left 1, 2, 3, and up 1. Move this key point 1, 2, 3, and up 1. Okay, and this key point would move left 1, 2, 3, and up 1. Okay, and then we'll draw in the shape of our base graph. Okay, so that would be our final graph. So you can see this method, the positives of this method are that it's quick, it's easy to do, okay, but the negatives are unless the graph has that very specific format, you won't be able to use this technique. So it has limited utility. Okay, so to graph other types of polynomials, let's start by talking about the end behavior of these graphs. Okay, so the end behavior only depends on the leading term of the polynomial. Okay, so we're going to look exclusively at the leading term. Okay, so we want to look at the degree and also at the coefficient, okay, the leading coefficient. So you might write the leading term like this. Okay, where n is the degree and an is the coefficient. Okay, so if the degree is even, okay, and the coefficient is positive, okay, then the ends of the polynomial will look like this. Okay, both ends will point up, and an example of that is y equals x squared. Okay, so that's an example of a graph that has that type of end behavior. So if your degree is even, but your coefficient is negative, right? We know that negative coefficients flip the graph, So that means both ends are going to point down. And an example of a graph that has that end behavior is negative x squared. Okay? Now, if you have odd degree, okay, and your coefficient is positive, okay, then the left side points down, right side points up, okay? And an example of a graph that has that behavior is the x cubed base graph, okay? And the last possible combination is if you have odd degree, but your coefficient is negative, okay? That flips the graph, we know, so that gives you that type of end behavior, okay? And an example would be y equals negative x cubed, okay? So that gives you an idea of how the ends of these graphs are going to point, okay? So let's talk about roots so that we can talk about x and y intercepts, okay? So the first thing we want to do is say, what is the root of a polynomial? Okay, so a root of a polynomial is an x value, and it gives the corresponding y value 0, okay? Now, these are also called zeros of a polynomial. Okay, and these are related to the x-intercepts, okay? You know that x-intercepts do have the y-coordinate 0, okay? So the difference between these and the x-intercepts is that this is just a value of x, okay? It's a single numerical value, whereas the x-intercept is an ordered pair, okay? So roots have a property called multiplicity. Okay, so the multiplicity of a root, for example, a number a, is the number of times that the corresponding factor, x minus a, appears in the polynomial, okay? So obviously it's going to be easier to see the multiplicity from the factored form, okay? And when you're looking for a multiplicity of a root, you really need to look at the factored form of the polynomial, okay? So let's do an example of looking for roots and multiplicity. Okay, so for the first one, we'll look at one that's already in factored form. Okay, so here's our first example. Okay, so to find the roots, you want to set the y value equal to 0 the same way you would if you were looking for the x-intercepts. Remember, those are very closely related concepts. Okay, and then we're going to look for x values that would solve this equation. Okay, so you're going to get one x value from each factor, right? So the x value that would make this factor equal to 0 would be 1. The x value that would make this factor equal to 0 would be -2. And the x value that would make this factor equal to 0 would be -5. Okay? And then for the multiplicity, we're going to look at how many times these factors appear in the factored form. So there's only one copy of x minus 1, so the multiplicity would be 1. Okay? There's 2 copies of x plus 2, so the multiplicity would be 2. And there's 7 copies of x plus 5, so the multiplicity would be 7. Okay? All right, let's do one more example like that. Okay. So if we're looking at this example, first we are going to set the y value equal to 0. Okay, and then we're going to list one root for each individual factor. Okay. Now, just like the previous example, you can do this by inspection. So we can see that this gives a root -3, this gives a root 1. But don't forget about x squared. This also produces a root. What would make x squared equal to 0? Well, that would be x equals 0. Okay, it's a common mistake to forget about that root, but it is very important. Okay, so then let's look for the multiplicity of these roots. Okay, so my multiplicity here is going to be 2. My multiplicity here is going to be 2. And my multiplicity here is going to be 4. Okay. All right. So now let's talk about what we're actually going to use these for. Okay. So the multiplicity of the roots, okay, has to do with how the graph behaves near that x-intercept. Okay. So if you have a root A, okay, then we know that that means A comma 0 is an x-intercept. Okay, right? They have almost the same meaning, okay? The difference is the root is a single value, the x-intercept is an ordered pair, okay? So if the multiplicity of A, okay, if that is even, okay, then the graph is going to bounce off. If the multiplicity is odd, then the graph is going to cross through. Okay, so some examples of what I mean by that, if this is the x-axis, okay, at a point A, you would have something that looks like this, okay, and if we're talking about crossing, if this is our value A, the graph would cross through like this, okay. All right, so this is all we need to graph a polynomial, so let's look at some examples of graphing. Okay. All right. Okay, so let's look at our first example. So we're going to look for the leading term. Okay. So what we want to avoid is actually having to multiply all of this out. That's not too bad for this example, but depending on how big the polynomial is and how many factors that can be really time consuming. So what we're going to do instead is we're going to look at what would happen if you did factor it, or if you did multiply it all out. Okay, so the leading term is going to come from multiplying the biggest term from each factor, right? So when you multiply x minus 1 times itself, you're going to have x times x, right? That would give you x squared. Then you would multiply it here one more time. That would give you x cubed. So for this example, our leading term is x cubed. Okay, and that tells us about our end behavior. So we have odd degree, okay, and a positive coefficient. Okay, so remember when we have odd degree and positive coefficient, it looks like y equals x cubed, and the ends are going to point like this. Okay, then we're going to look for our x-intercepts, okay, our roots with multiplicity. Okay, I guess you still want to be able to see the polynomial. Okay, so the roots, those are going to be -3 from this first factor, okay, and 1 from the second factor. And then we can look at the multiplicity, right? The exponent here is 1, so that's our multiplicity. Exponent here is 2, that's our multiplicity. Okay, so because our multiplicity is odd, this is going to cross. Okay, and because our multiplicity is even, this is going to bounce. Okay. All right. So one last thing, we're going to look for the y-intercept. Okay. Now, you guys know how to do this. You let x equal 0. Okay, so we're going to do that for our original polynomial. So we'll have 0 plus 3 times 0 minus 1 squared. Okay, and that'll give us y equals 3. So I have my ordered pair 0, 3. Okay, now we have everything we need to create our graph. Okay. Okay, so remember our roots were -3 and 1. So on our graph, we're going to mark -3 and 1 as my x-intercepts. Okay, remember my y-intercept was 0, 3, so I'm going to mark that. Okay, and then let's double check our end behavior. The left side is going to start down. So just like whenever you graph, you want to start on the left, we're going to start here on the left. We know that the left end points down. Okay, so now we're going to approach that x-intercept, okay, and we're going to check what happens at this x-intercept. Okay, so at -3, it's supposed to cross through. So we're going to go to our graph, and we're going to cross through that intercept. Okay, then the only other thing we know is that our graph hits this point here. So we're going to draw the graph hitting that point. Okay, and then we know that we have to come down because we have to hit this x-intercept. So the graph is going to go down. We're going to approach that x-intercept and check that behavior at that point. So at 1, you can see it's going to bounce off. So we go towards that point, our graph bounces off and goes back up. Okay, and then we're going to check that that corresponds with our end behavior. Yep, the right end is supposed to point up. So this is our final graph. Okay. All right, let's do another example. Okay. Okay, so again, the first thing we want to do is look at the leading term. Okay, so our leading term is going to come from multiplying the largest part of each one of these. So we'll have x times x, x times x, right? So that's 1, 2, 3, 4, 5, 6, okay, with the negative 2. So we'll have negative 2x to the 6th. Okay, so this has odd degree. Okay, and it has a negative leading coefficient. Oh, I'm sorry, 6 is even, has even degree, okay, and it has a negative coefficient. Okay, so even degree, negative coefficient, both ends point down. Okay, then let's look for our roots. Okay, we want to be able to see that polynomial. Okay, so remember, don't forget about this when you're looking for the roots. This gives you the root 0. Okay, then x plus 3 is going to give me the root negative 3. This will give me negative 1, and this will give me positive 1. Okay, then I'm looking for my multiplicity. This has exponent 1, so I'll have multiplicity 1. This also has exponent 1, so I have multiplicity 1. This has exponent 2, and this also has exponent 2. Okay. So now my behavior, this is going to be cross, cross, bounce, bounce. Okay. Again, I wanted to emphasize that you're looking at whether the multiplicity is even and odd. You're not looking about whether the root is even or odd. Okay, let's look at our y-intercept. Okay, you would plug in x equals 0. Okay, so y equals negative 2 times 0. Okay, now it doesn't really matter what all of these things turn out to be, okay, because you have this 0 here. This is definitely going to be y equals 0. So we're going to have the origin as our y-intercept. Okay, all right, so now let's start to form our graph. Okay, so first we're going to mark all of our roots. So we had 0, negative 3, negative 1, and positive 1. Okay, and that takes care of our y-intercept also because that was the origin. Okay, so now we're going to look back at our end behavior. There it is. Okay, and we're going to start with the left end pointed down. So here we go. I'm going to start with my left end pointed down. Okay, and then I'm going to approach this first x-intercept. Now I'm going to look at the end behavior at this point. This is negative 3. Okay, so at negative 3, my graph is going to cross through. Okay, so I'll cross through at that point. Okay, now I'm just drawing my graph going up, but I know it has to come back down because of this point here at negative 1. So what's going to happen at negative 1? Well, at negative 1, the graph is going to bounce off. So as I approach that point, I'm going to draw my graph bouncing off. Okay. Now what's happening at 0? At 0, you can see that it's going to cross. So I'm going to cross through at 0. Okay. And then at positive 1, okay, you can see that it needs to bounce off. So I'm going to show it bouncing off that point. Okay, then I'm going to double check my right end behavior to make sure they were supposed to both point down. And that is exactly correct. Okay, now if you find that the way your ends are pointing from your graphing isn't matching up with what it's supposed to be, that means that you've made a mistake. So either you have a mistake in the behavior near your x-intercepts, or you have a mistake in the actual endpoint, but they should always line up. There should never be a case where you can't make the way the x-intercepts look line up with the way the ends are supposed to look. They should always go together. Okay? All right. Now, there's only one more thing that can happen here, okay? And it's when you are trying to find the roots, okay? You might be in a situation where the polynomial isn't already factored out, okay? So let's look at an example of this. Okay, so if you have something like this, okay, what you need to do to find the roots is factor this. Okay, so we're going to start by doing what we always do to find the roots, which is setting it equal to 0. Okay, and now we're going to try to factor this. Okay, we have 4 terms, so we're going to try factoring by grouping. Okay. Oh, before we even try factoring by grouping, I take that back. If you look at these terms, all of these share a common factor. So I'm going to pull out my common factor of x squared before I do anything else. Okay, and then with what I have left, now I'm going to factor by grouping. Okay, factor out my common factor of x plus 1 here. Okay, and then I'm left with minus x squared plus 9. Okay, now you can do this a number of ways. You can factor out the negative sign right now. You can reorder the terms, but I'm going to factor out my negative sign. Okay, so that would change this to positive x squared, and that would change this to negative 9. Okay, and now you can see this one is the difference of squares. Okay, and now I have it in completely factored form where I can just read off the roots. Okay, so my roots would be 0, -1, 3, and -3. Okay. All right. Now, the very last thing that can happen with this is, what if you have a polynomial that doesn't factor by grouping? Okay, so let's look at an example like this. Okay, so you can look at this, you see there's no common factors. It's not going to factor by grouping. Okay, so in this case, they'll usually give you one extra piece of information. Okay. Okay, now you guys will see this in a supplement. It tells you what one of the roots is when you have something that doesn't factor like this. Later on in 370, you guys will see a way to avoid needing this information. You'll talk about how you can get the roots without knowing. Okay, but for right now, you guys will see that if it doesn't factor in some way that we've already talked about, it will give you one of the roots. Okay, now all you know is that 2 is a root. Okay, remember that means x minus 2 is a factor. Okay, so we know one of the factors of this polynomial. Now, this is a lot like a factor tree. If you have some huge number, you know one of the factors, what do? You split the number up into the factor that you know, and then you divide it to get the other factor. So that's actually what we're going to do here. We're going to divide this polynomial okay, using polynomial long division by the factor that we know, okay? So I'm just going to divide this. This times this will give me x cubed minus 2x squared, okay? Now remember, you are subtracting these, so when you subtract this, you're getting minus a negative, which is plus. So that would be plus 6x squared, okay? X into 6x squared is going to be 6x. This will give me 6x squared. Okay, 6 times negative 2 is negative 12. Okay, and again, you're subtracting. So that's 0, negative 7 minus negative 12, right? Or negative 7 plus 12. So that would be 5. Okay, x into 5x, that's 5. Oh, I'm sorry. Okay. So what I was doing while you were looking at the wrong part of the paper, here I had 6x, so when you subtract, right, you have negative 7x minus negative 12, okay, so that's negative 7 plus 12, which gives me this positive 5, okay? So now x into 5x, that's 5, and then I'm going to multiply 5 times x minus 2, and I get 5x minus 10, okay? Subtract these, you get 0. Now, you should always get 0 as your remainder because you know that this divides evenly, okay? So what I know now is that my polynomial can be written as x minus 2 times x squared plus 6x plus 5, okay? And now this is a regular quadratic. I can factor this using normal methods. Okay, and now the factored form lets me read off the roots. Okay, so my roots will be 2, negative 5, and negative 1. Okay, if you guys need a review of how to do this, the polynomial long division, okay, I will try to link you to another video where they explain how to do polynomial long division, but this should be familiar to you from your algebra class, okay? So I encourage you guys to do the S.12 worksheet that's posted on Canvas and also to watch the other video for today, which is S.13. Okay, see ya.